My name is Allison Herrera, and I'm one of the account managers here at Summit Interconnect out of our Hollister facility. And we are going to be discussing today how PCBs are manufactured. We always get a lot of questions, especially on the sales side, regarding capabilities and technical details, but a lot of people also need to know how we're actually manufacturing the boards. So that's the reason for today's webinar. And before we get started, I want to go over a little bit of the logistics. Everyone always wants to know if they will be provided a copy of the recording. And yes, we will be emailing out a copy of this webinar tomorrow. So if you've registered, which you have, you will be receiving that to your inbox. And then just some of the practical things to go over. We have a chat function at the bottom of the screen that you can utilize at any time during the presentation. If you have a question, just ask in that little chat box, and then we will try to get to it during the presentation. And there'll also be a time for questions at the end. But I encourage you to go ahead and just ask the question as it comes up. And then today, I have the pleasure of introducing our speaker, which is Aaron Kennedy. He has been with Summit Interconnect for 8 years. He's the engineering manager at our Anaheim facility, and he's built his career around innovation and leadership in the PCB industry. He's been with Summit as a CAM engineer and then CAM supervisor, and now as the engineering manager of the CAM department. And in these roles, he's overseen process improvements, managed complex engineering projects, and guided technical teams to ensure that Summit reliability circuits that meet the most performance standards. And before joining Summit, Aaron gained his experience as a CMM programmer and as a CNC machinist. So I want to introduce him, and I'm going to go ahead and pass it off to him to begin. Well, actually, no, because I have one more person that I need to present. So this is Aaron. And then we have another person that's joining us on the call who you've seen before if you've been on any of our webinars, and that's Jerry Partita, VP of Technology here at Summit, and he's been in the industry for more than 30 years. In his current position, he is focused on HDI, high-speed digital, flex, rigid flex, and RF and microwave PCB fabrication for military and commercial industries. He is also a certified IPC trainer and a member of the IPC 6012 and IPC 6018 review committees. So thank you both, Aaron and Jerry, for joining us today. And I'll go ahead and hand it off to you, Aaron.
Yeah, no problem. Allison, do you want to do the...
Oh, yeah. Yes. So I'm going to talk a little bit about Summit. We are the largest privately held PCB manufacturer in North America. We have 7 North American-based facilities, and we have a lot of different sites, so that way we can find the best fit for whatever project that you're working on. We focus on providing the best customer experience with easy ordering. We try to make it very transparent. Whatever we're experiencing with your build, we try to communicate that. And then we have a broad range of PCB product capabilities, everything from flex, rigid flex, high density interconnect boards, from prototype to production, we can support your projects. We have an extensive amount of quality certificates also that covers all of our, basically, if you need anything from prototype to flight production, we can support you. And then this is just the list of the types of PCBs that we manufacture. Of course, rigid boards, high layer counts, stacked microvias, back drilling, sequential lam, heat sinks, copper coin boards, and we also offer very quick turns for prototypes. So that's for the rigid. For flex and rigid flex, we can manufacture various types of rigid flex and flex boards. And there's just a little list there that kind of discusses the types of flex and rigid flex products that we offer. And then for the RF and microwave products, we have a wide range of materials that we offer. For different types of designs. We can do plated cavities, edge plating within those cavities, mixed material stack ups, buried resistors. So if you have any of those types of applications, we can also support that. And then, of course, the semiconductor and ATE types of products we can also support. So that's just a very quick overview of the types of products. And if you have any questions, we can connect you at the end with one of our account managers that can help you get a quote on a project.
Thank you, Allison. Appreciate it. So this is going to be a very high level overview of some of our manufacturing steps in a PCB board shop. We broke it down to about 20 key steps. We have any of our travelers, we have anywhere from 150 to 250 process steps. And I could talk for an hour on each one of these process steps individually, but we're going to go through them a little quickly just to give you a very high level of how a PCB board is manufactured. So it all starts from getting design files from the customer, right? Customer sends in a one-up design, and we will go through our DFM checks. The front-end engineering is split up between planning and CAM. Our planning engineers are going to review all the documentation. They're going to select material and panel size. We're going to create material stackups and calculate impedance if impedance is required. And then they're also going to use all that information to create our manufacturing travelers, right? Now, at the same time, CAM is going to import the customer data. We're going to do a net compare and run through our DFM checks to make sure it was designed for manufacturing. We're going to prepare the data. We're going to panelize on a production panel. Some of our production panels range from 12 by 18 all the way up to 24 by 36 in our Anaheim facility. We create test coupons and customer coupons and place them around the board for IPC and for customer reasons to make sure we can validate the PCB without destructively testing and losing our PCBs on our manufacturing panel. So we're going to go through that. One of the first steps is choosing our base material. Usually we have an IPC slash sheet to go to. An example here is 4101 or 4103. You can choose we're going to choose different laminate cores, different prepregs, and different bond plates and cover lays and flex material if that's applicable. Our laminate cores are cured resin and glass fabric with copper on each side. Prepreg is an uncured resin, glass fabric and no copper. Different IPC slash sheets have different material properties, whether it's brominated or not. We're going to go also and choose our copper foil for IPC 4562. It's a good example. Our copper foil ranges from a quarter ounce all the way up to about 5 ounce copper. All of these different attributes are different ways to build our PCBs, right? So this is what our planning engineers are going to go through, and they're going to go through the customer requirements on the drawing and or specs, and then we're going to choose the best fit material for that product. This is an example of our stack of creation. So we're going to go through and we're going to create the backup in our ERP system or our stackup software. We're going to go through the different resin content, thicknesses, and TGZ values to make sure we get the best product for that requirement. And if we have any impedance requirements, we have our own in-house impedance calculators. So different materials and different copper weights and line thicknesses can affect the impedance. Right? So as far as our CAM engineer, CAM stands for computer aided manufacturing. We start with a one-up design from the customer here. And then we are going to go through and we are going to step and repeat and panelize these on a panel. We are not allowed to edit customer data, but we do add edge compensation and some manufacturing compensation, right? Because what the customer sends in, we have to slightly modify that data or comp it to get that finished product, right? So we're also going to create coupons, place them around the panel so we can destructively test these at the end, and we don't affect the PCB, but we can ensure that you are getting good quality product. So one of the first steps after planning and CAM is done, we're going to release that material to material issue. Each individual core gets its own traveler, and that traveler hits the floor and we'll start at our clean and coat, right? So the core laminate is cleaned with an acid dip prior to photoresist process. Prepreg sheets get put into lamination, but prior to lamination, they will get drilled or punched with the corresponding tooling. So we're gonna run that through the acid dip and photoresist, and then we're gonna coat both sides through it with our hot roll laminator with resist on top and bottom without an image on them. Then it goes into our LDI room where we print that image that we received from the customer that CAM is now stepped and repeat on a manufacturing panel. So after the resist is laid down, we selectively expose the image with an LDI laser. The LDI laser is going to expose the resist with the circuit pattern. The circuit pattern will become this dark purple color. This dark purple color will be the remaining resist. So then after it comes out of the LDI room, it goes through our DES line. DES stands for develop, etch, strip. We're going to develop the resist that is not exposed, almost like a picture. Then you're left with the resist that is protecting our copper image. We're going to chemically etch away that copper, and then at the very end, we will strip away that remaining resist, and then you are left with just a pattern that is needed, right? So here's an example of that. Here's a solid interlayer panel coated with resist. It goes to our laser direct imaging machine. And then now you have the exposed resist on the third picture on the right. All of the dark image will be protected and the light image will be chemically etched away. So the resist is stripped at the end after we chemically etch away the copper that we don't want. The copper pattern remains. Finished layers get post-etch punch in preparation for the next process, which would be interlayer lamination. Here's an example of our DES line. Like I said, develop, etch, strip. Here's a completed interlayer where you have the remaining copper of the image that we wanted, and we chemically etched away all the copper that we did not want all the way down to the base laminate. And then here's a post-etch punch target where the 4-slot will be punched on the far right. And here is your image and your copper etched down to the bare laminate. After our DES line, everything goes into AOI, which stands for Automated Optical Inspection. Now, this panelized data is loaded on this machine, and the machine is going to go through and look at every single step and repeat PCB on that panel. It is not doing measurements. It is looking for shapes and features. So it's looking for copper that should be connected, that isn't, or copper that is connected that should not be. Also at that stage, we will do on a separate machine, we'll do a FA and AQL of minimum line and space. So after all of the layers have gone through AOI and we ensure that everything is at the correct quality, we will go into interlayer lamination, right? So in lamination, we are going to be lining up all of these layers together, putting pre-preg in between to put it into a hot press to cure this into one final PCB, right? So before we do that, copper is roughened by oxide to promote adhesion for the lamination process. We put laminate, pre-preg, and outer layer copper layers are stacked up for lamination. The final result, often referred to as sub or a final panel, is what comes out of the hot oil presses, usually for around, it's in the press for usually around 4 hours at that time. Here's an example of the interlayer, one interlayer that is run through our oxide line, or some call it Cobra bond. So it oxidizes the copper and it gives a rough surface for the pre-preg to hold on to, so we have good adhesion and no lam voids, right? Here's an example of our lamination layup. So you can see we have a steel plate at the bottom with 4 pins. Those 4 pin locations were punched on the interlayer machine by our 4-slot punch machine, aligning to targets on the etched layer. We're going to lay up one layer at a time with pre-preg in between, and we do this all the way through, whether you have a 3-layer, 4-layer, all the way up to about 40 layers we offer, and this is repeated over and over until we get that final structure. Here's an example of our lamination press. So after these books are fully laid up and complete, that steel plate, there will be one on the top. That steel plate will go into this hot oil press. It is pressed under pressure. A good example, it depends on laminate and material, but a basic example will be about 350 degrees under about 300 or 350 pounds of pressure, right? Now this temperature and pressure varies based on the material chosen at the front end. After it comes out of lamination, we are going to put it on our inspector machine, and we are going to X-ray our targets that we have in all 4 corners of the panels to make sure that these cores did not move more than we predicted at the beginning. So we did give each of these layers an interlayer scale. After that, we're going to put it on the X-ray machine to make sure that predicted scale value was accurate. Now, if we can ensure that we can drill through all of these pads without breaking out or missing a pad, we are going to move that to drill, and these are going to drill through all of the panels, through all of the layers, and we're going to get that final hole structure that we're looking for. An in-process coupon is drilled at the drill step. We X-ray that to make sure that we do have the correct registration. This is an example of one of our mechanical drill machines. Some of these range between 5 and 6 spindles depending on the table sizes, and we can drill 6 panels at the same time. If the final sub or laminate is actually very thin, we can sometimes do this too high as well. After our drilling process, we have to prep this hole for plating, right? So when we drill it, we get a little bit of smear. Smear is the resin melting a little bit, going, and you can see in the picture here that it is that after we drill this image, some of this prepreg resin melts and it will get on this copper. So when we go through our electrolysis line next, this pad will not get copper. So we don't want that. So we will send that through our what we call plasma, and we get our etch back values. So the plasma is a gas that will attack organic material, which is the laminate, and it'll actually etch it back slightly so we can get nice three-sided connection to our electrolysis copper, and that maintains good pad connection, which will maintain good interlayer connection, and then you can have a good strong electrical connection when we go through this process. So after our plasma process, here's an example of our electrolysis. A conditioner charges the side walls, the palladium is attracted, then the reaction allows copper to start plating on the sidewall. A thin layer of electrolysis copper is chemically plated and on non-conductive material. So you have this thin layer of electrolysis copper going down the entire length of the hole wall. After we have this thin layer of base copper, because that electrolysis is very thin, it ranges between 2 and 3/10 thick, sometimes even thinner, but usually around 2 and 3/10 thick. After that, we will go into our, so here's an example of our electrolysis line here. After that, we will print our outer layer image. Now it's a very similar process to our inner layer printing, but we will print this in a reverse polarity because you cannot get resist to go down the length of a hole wall. So we print it in the opposite polarity so we can plate that hole wall with tin, and tin, we will use tin as an etch resist, and the resist dissolves over the pattern to be plated, right? So here's an example of our outer layer image, one of our outer layer imaging machines. We're gonna plate that bulk of the whole wall electrolytically with electrolytic copper. So we clamp the edges of the panels. This is still solid copper, top and bottom, and now we have that thin layer of electrolysis. So this is now a conductive hole, and we will plate that bulk of your copper at this point in time. Usually it ranges between 1 and 2 mils thick, depending on customer requirement. Here's an example of our copper plating mats here. After that, this is where, like I was saying, we're going to plate our tin. The tin is going to be plated on the outer layer image on the outside, and then plated down the length of the whole wall. Everything that is not protected by tin will get etched away. So this resist is stripped off. Then we will chemically etch away the copper we don't want all the way down to the base laminate. The copper that is underneath the tin will be protected, and then after that, we will eventually strip our tin off, and then you're left with that outer layer image with plated through holes that span the length of the board. Here's an example of that. Here's the tin, and then we will etch down all the way down to our base laminate. So you have the base foil, and then the plated copper on top with the copper plating going down the whole wall. Okay. Here's an example of our tin plate, strip and etch. So here's our tin plate with the resist on. This is after we strip the resist, so everything that is silver in color, protected by the copper, will be, and then you are left with the etched copper here, just like this. After that, the resist and the tin are both stripped from the panel. So we do not want that tin shipping to the customer. This will be shipped just with the copper, other than the final surface finish at the end. So after we have our outer layer image, we are going to be moving to solder mask, right? Our solder mask will protect the laminate and the copper that is not exposed from the final image that is not being assembled to. So this is the picture on the left is an example of a solder mask clearance with solderable pads. Then the middle image is a dry film tent. So we can actually dry film tent a holes to prevent anything from getting inside, and we will get it covered. And then we also offer solder mask plugging. Well, we will actually fill the hole with solder mask to prevent any expansion of gases and stuff in between. Here's an example of that outer layer solder mask. Um, the picture on the right has solder mask clearances with BGA pads. So a customer will receive this board and assemble to these exposed BGA pads. And then you also see the buried vias that we tented with solder mask to protect them from any chemical exposure or any oxidation. So after that, we have to go out for our surface finish. Our surface finishes range from ENIG, AnyPig. We also offer hassle and solder. So these are all common finishes within the circuit board industry. Some of them are electrolytic plated. Some of them are immersion processes. But any exposed copper will get this surface finish, and the final finish is applied to exposed copper to protect it from corrosion over time. After our solder mask process and our outer layer surface finish, we will go to ink legend. Ink, a lot of this is often referred to as silk screen because this is a legacy term because we used to hand screen all of this legend on. Most of this legend is done with a sprint machine now, so it's inkjet printed directly onto the panel with an inkjet printer. Well, most of the features are for our customer. It gives them mounting points for where they're going to assemble their product. We will also put our PCB serialization and traceability at the silk screen at this time, right? Okay. Here's an example of one of our Sprint Legend machines. This is a Sprint 120. The panel is placed on the machine. The machine aligns to fiducials on all four corners of the panels, and then we will print the legend. This is an example of the coupon legend on the far right. It has part number, cage code, lot number, and our date code of when it was plated. We also add serialization at this point as well. After our inkjet is done, the panels are getting close to final at this point. So they will go into electrical tests. Some of our boards are electrically tested in panel form. Some are tested in piece form. It depends on the construction of the PCB at that point. So our rigid flexes are a lot of the times done in panel form because they're too flexible. Now, if you have a rigid PCB that is of good size, we can also test those in piece form. We are going to test every single point on the circuit board, compare it to our customer net list, and ensure that you have no shorts, no opens, and that this board is going to electrically function the way it is supposed to. After our electrical tests, they will go into our route department. So we are going to route these individual PCBs out of the manufacturing panel. We also route the coupons at this point. We're going to send the coupons to our cross-section lab so we can do that destructive testing. We're going to route these boards, and these boards are going to go into final QC after this. Before final QC, they're going to be put on a CMM machine so we can measure 100% of those drawing dimensions to make sure that the customer is getting the board that they ordered. This is an example of our CMM and our final inspection department, right? So you can see our CMM machine. We are going to measure all of those dimensions. We can actually output a file from CAD to the machine that it'll automatically measure all of the data points going around with a CNC file. Our final inspectors, we're going to inspect this to IPC 600 unless otherwise specified, like a customer spec. Now we're going to inspect all of these boards 100%. At this point, they're going to look for any handling defects, any FOD, and anything that could have happened, scratching, dents, FOD, or anything underneath the mask at this point to make sure that the boards going out of final inspection are at the best quality possible. Okay. At that time, usually done in conjunction, the coupons are sent to our cross-section lab. So we put the smallest hole and the largest hole size on this coupon with your smallest annular ring. That smallest annular ring represents our registration per IPC. So we will, per IPC, we'll do 2 coupons off of every panel on cross corners. Like I said, this requirement is pretty standard. Now, if you have a customer requirement that requires more cross-sectioning, we will also do that as well. So they're going to measure the thickness of the copper in the hole wall. Well, you can see this measurement here. We're going to measure the amount of pad sticking out on either side to verify our registration. And then we will also verify any surface plating at this point in time. So these are done on every single production panel. So if you have a lot of 24 panels, you have at minimum 2 cross sections per panel are going to be done on every single production panel. Sometimes these pucks are shipped to the customer. Sometimes we just ship pictures, but all of this is done for every single every single lot that we run through our factory. I did go through this relatively quickly. I understand that this is a very high level view. We had a lot of slides to go through, so we could speak to any one of these slides in detail upon further requests, but we wanted to give you a very, very high level of how a PCB board is made. Now I'm going to
So,
open up for any
oh,
questions at this time.
yes, so we have quite a few questions that have come in while you were talking. So I'm gonna just begin from the first one. It says there is a big range on slash sheets. So we're talking about material. For example, IPC 4101/126 covers isola products from 378 jar to iSpeed. How would I use a slash sheet call out if I wanted an iSpeed type material? Would I just call out IPC 4101/126 with a DK of less than 4, or is there a more preferred way?
So our preferred way is with the slash sheet. So with the slash sheet and the DK value, that does narrow the range of materials, but customers always do have the option to call out a specific material if there is a specific need for this design. So you can slash sheets are the preferred method because it gives the manufacturer the 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 option to choose many different materials under that umbrella, but you do have the option to call out a specific material at any time, and we will adhere to that. I hope that answers your question.
Okay, and then the next question is what panel sizes do you have available and how will the size affect the price? So I think that one kind of goes, you could answer to the production side. On the quick turn side, we prefer to keep one panel size because that enables us to move very quickly for prototype quantities, and also because a lot of the cost is in the labor, not so much just the material.
Yeah.
So I know it's different for the production side because a lot of times you're looking for registration on, I'll let you talk about the production side of things.
Yep. So depending on complexity, we will determine what panel size best fits, but the ultimate goal is to fit as many PCBs on a production panel as possible. When you put more PCBs on a production panel, it makes it more cost effective for us, and it does give you a better price in the end. So a one-up panel versus a panel that has 50 boards on it will be significantly different in price. Now we offer as small as a 12 by 18, and we do go all the way up to a 24 by 36 in the Anaheim facility. The Anaheim facility is special where they do oversized panels up to 24 by 36, but all of our other shops do offer 18 by 24 and a 21 by 24 as well.
Okay. And then another question. So is the point of the top and bottom copper planes to protect the laminate from plasma in the smear removal step?
So I think the question is they're asking, does the outer layer of copper protect that?
Yes. So the outer layer copper, when it goes through plasma, it does protect the laminate from getting attacked by the plasma. The main goal of the plasma is to clean the whole wall, so we can get a nice thin layer of electroless copper sticking to that rigid laminate. Now, the solid copper on top and bottom will protect the outer laminate from that.
Okay, next question. I see differing opinions online regarding percentage of copper distribution per layer. Is there a percentage that a PCB layer should have covered by copper that will reduce etching problems and delamination?
So there's not a specific percentage that is preferred. The main thing that you have to consider is balancing the copper, right? So if you have a plain layers on the top half of your board that are 60 to 80% copper, and you have signal layers in the bottom half of your board that are around 20% copper, that copper restricts and holds the material. So if you have an unbalanced construction, you're gonna create bowing in the PCB, and you're gonna create a bow and twist issue, and it becomes an assembly problem and a manufacturing problem. So in short, the answer is not to pick a specific percentage of copper, is to keep it as balanced as possible throughout the build.
Next one is when and or how is VIPO done or VN pad plated over?
So VN pad plated over. So at that point where it goes, we showed a board with final drill. So if there is via in pads, that will right after our electrolysis step in our plasma, we will separate the filled vias and the through vias. We're going to drill those filled vias first. We're gonna drill them, plate them, then we're going to fill them with our non-conductive epoxy. We will sand the epoxy to make sure we have a nice flush surface, and then they're going to go in, and we will plate over that to fully seal in that via, and then we'll go back for an additional drill step, drill in our plated through holes that are going to be open at that point.
Must specify. You have to specify.
Yeah, but you have to specify that on the drawing. If it is not specified to have via and pad, we're going to assume all holes are open.
Okay. All the information for the AOI and electric automated test is already embedded in the Gerber files sent by the client. I think they're asking,
Yeah,
is the information for AOI and electrical test already embedded in the Gerber data sent by the customer?
Yes. So for electrical tests and for AOI, so I'll do AOI first. For AOI is going off of just images, which we are using that image from the customer. The only difference is the AOI is using the image that CAM gave them because it is stepped and repeated on a manufacturing panel. So yes, that is provided from the customer. And then the same thing at electrical test. The net list is provided from the customer, and then we will test that compared to the customer net list. This is all done on the customer side of things. When they do design, they will design in some sort of CAD software, whether it's Genesis, CAD/CAM, or one of the many other softwares out there. They will design pads, traces, and create a net list from that. That net list is sent to us, and we have to maintain that net list.
Okay, so I'm not sure what this question is asking exactly, but it's saying, is electrical test before routing the same as what you would do? Is electrical test before routing same as what you electrical test you might do during inspection or before shipping to your customer?
Yeah, so whether we do it in panel form or piece form, it is really design specific, right? So the preferred method is to do it in panel form. Now, if test has a lot of work at that time and route does not have a lot of work, and you have a rigid board that is big enough to put on a testing machine, then we will route that board out first and then send it to our tester after. So whether it's done in panel form or piece form, it won't affect the test results. The only caveat to that is if there is controlled depth milling, especially on our rigid flex product, that electrical test is always done after the controlled depth milling, just in case one of our operators went too deep on the milling and cut a trace. We want to be able to catch that electrical test, which will create an open.
Okay. Other questions I've had, when laying out traces, I've been instructed to avoid making acute angles so that an acid trap is not formed during manufacturing. Is this a valid concern for modern PCB manufacturing?
I'm sorry, can you repeat that, Allison? You kind of cut out.
Yes. When laying out traces, I've been instructed to avoid making acute angles so that an acid trap is not formed during manufacturing. Is this a valid concern for modern PCB manufacturing?
Yeah, it is a valid concern, especially on plated layers. So when we lay that resist down, creating a 90-degree angle or a sharp turn does create challenges with that resist to be able to lay down in that corner. When you create a curved turn instead of a 90-degree angle, it gives that resist better chance of laying down, so we don't create a different short or lifting resist and create excess copper on that outer layer.
Okay. The next question is, where are blind or buried vias added in the process? How many steps duplicate?
Okay, so what I showed you in the presentation is a single lamination job. So if you have a blind or buried via, it is going to follow all of those exact process steps with the exception of solder mask and legend. So we are gonna laminate those subs together. An example, if you have a 2 to 10 sub, so we're gonna laminate all the way layers all the way up to 2 and 10. 2 and 10 are treated like an outer layer at that point, which is the outers of our sub. We call them plated layers here. So we're gonna drill all of those buried vias. It is going to go through electrolysis, plating, and fill. And we are going to go through that. We even have the option to do an in-process sub test, and it will go through the entire manufacturing process, like I said, with the exception of solder mask and legend. Then it will return back to lamination, where we will laminate those 2 outer layers on the outside, or another half of a sub if there is another.
Sure, we can test the buried.
Yeah, we can test buried vias, but we cannot test. We cannot electrically test the blind vias.
Okay. Why would you use prepreg plus foil instead of a core for outer layers?
So that's a very good question. So the reason why we prefer to use prepreg and foil is because if you have a core for the outer layer, the outermost cores are what's touching the hot lamination plate when it goes into lamination. And if there is a copper layer on the inside of that core, it is restricted from the movement because it is seeing the most heat. So registration becomes a big issue. Where if you have prepreg and foil, there's no image on the inside of that foil. That foil is laminated to the outside, and then we will eventually print that outer layer at the very end. So it becomes a very good registration.
So this is Jerry Partee. I'm going to interject here. So when you do cap core construction, especially thin core cap core constructions, the yields on building that board will probably drop anywhere from 10 to 30%. Foil lamination has superior registration. And as Aaron nicely said, because of the movements of the prepreg trying to shrink and the outer layer lam plates are trying to grow, that top core has weird thrust happening and it doesn't always. So anytime you have a cap core construction, when we did a webinar back in November about this, it will lead to lower yields. And if you have blind vias with cap cores on the blind vias, then you double the failure rate because of this. So fabricators like ourselves are always looking to have a design with foil lamination because it has superior yields.
Yeah, thank you, Jerry.
Okay, so,
I'll answer the next one. The question was, could we recommend a third-party software to do DFMs? So the Mentor Graphics NPI, formerly known as Valor, is a great tool to analyze data, to look into the design, to see if there's any design for manufacturability issues. We also use Integrator from Sims, which does a really great analysis. We've adapted it here at Summit. And there are other packages available out there like Frontline's Insight, which we have had in the past as well.
Okay.
We also have DFM reviews as well.
What's that?
We also offer DFM services within our company as well.
Hang on a minute. I'm not sure of this question, but see if Aaron can get it. Go ahead.
Okay. It says, is plasma a good and active method for treatment?
Yes. So plasma is a good method to treat the material before it goes into electroless copper. The only caveat with that is some of our exotics, like example, the Rogers 4000 series, or some of our PTFE materials, it attacks it a little bit harder. So we have to accommodate for that on our side. We have to use a different plasma recipe, but generally speaking, it is a good way for treatment.
Sometimes necessary.
And it's necessary. Well, yes.
Some cases only one.
Yeah.
Okay. Assuming the final outer layer thickness is 1 mil or 1 ounce of copper, what is the optimal foil size to start with? What other factors affect the selection of starting foil?
So we have a couple options here. So we will have to plate copper. So if 1 ounce is the finished goal, we're going to start with something smaller than that. Now, our typical go-to is starting with 1/2 ounce copper. Now, the caveat with that is if you have very, very tight spacing and we have to plate up this copper, we want to start with as thin as copper as possible. So that's when we will start with our 1/4 ounce or our 3/8 ounce of copper, is because if we have tight spacing to adhere to, we need room to plate the copper without creating an electrical short.
We have copper. That's compensation.
Yeah. So we have to and we also have to compensate. Like I mentioned it at the beginning in CAM, we have to compensate this artwork. A good example of that is if you have a 10 mil line on your outer layer, that image is actually going to be bigger than that. It could be up to 11.5 mils because we have to account for the thickness of the copper. Now, after that's printed and plated, when we etch down, we are going to etch down to that finished size as close as possible.
Okay, another question. Will you provide impedance calculation tools for the customer to determine the optimal trace width and stack up during the PCB design process?
Yeah, so we usually receive these boards after design. So after the design comes in, customer has their calculated line and trace width. Now after we build our stack up, we might use slightly different prepreg values and core thicknesses. Now after we do that, we will run our own impedance calculation, and then we will let the customer know if we have to change that line width outside the allowed tolerance, right?
And usually that happens too on the sales side. So you can reach out to your account manager, request whatever impedance you are looking for, and then we'll provide a stack up to you that you can work with. One thing to note on that, though, is that sometimes once the design is finalized, there are changes that will be made by engineering on the stack up. So it's not that it's 100% set in stone, but definitely reach out to your account manager and we can help provide that information. The next question, can you go over how stacked micro vias would be used to make blind or buried vias?
So yeah, so stacked microvias, they allow the customer to create a tighter BGA and smaller pitch, because when you the microvias are a lot smaller and you can stack them on top of each other. Now we don't recommend stacking more than 3 high. We are exploring other materials that allow for a thicker stack. Now when we have stacked microvias, we will run this through a simulation with a software we call Gauss. The Gauss simulation will actually simulate reflow and see how reliable those microvia connections are going to be after the material expands.
And this is Jerry Partita. So there's also with the Gauss stack and certain materials that we know work well for microvia reliability, that we are simulating and building boards and decoupon testing them up to 4 stack microvias and passing with decoupon OM reflow results. So if you want to know more about that, please get a hold of us and we'll be able to share that with you. Probably not in this presentation, but maybe in the future. Yeah.
Okay. And then the next one is, do you recommend copper thickness only on top and bottom or all layers? I'm not sure what that means.
I don't really understand the question. So
they're asking, do I only have to specify the copper on the outer layer?
Oh, no, yeah. So you do have to specify the copper all the way throughout the inner layers.
If you don't, we can just assume it's half ounce and do whatever we want.
Yep. Yeah. So if you don't specify, we're gonna choose the easiest one to manufacture, which would be half ounce print and etch, and that is the copper you're going to get. But if you specify, we will go all the way up to about 5 ounce copper here.
So the reason why I love this question is that most people don't know in IPC 6012, 6013, and IPC 6018, if you don't specify certain criteria about a board, there are default selections or attributes that we can pick. So if you don't say anything, we can use half ounce.
Yep.
If you don't say anything, we can now use ENIG as a surface finish. So if you don't specify, please make sure you know what are the default attributes a board fabricator can pick, because you may not get what you're expecting in your board if you don't specify it, because it is technically legal for us to pick anything from that attributes default list if it's not specified on the drawing. Allison, can you let people know about the recording? Somebody just sent a question.
Yes. So we will be emailing the recording out to everyone that registered. So if you're on this call, you'll be receiving a recording of the webinar probably tomorrow or sometime this week. So you can be keeping an eye out for that. Okay, the next question is it preferred to send the Gerber or the ODB++? And also, is it preferred to send the 1-up Gerber with fab spec with our fab guidelines, or to send our own quick fit array with rails?
So that's a very good question. So our CAM department can handle both ODB++ and Gerber. ODB++ is the preferred method, though. It has it makes our job a little easier, and it has more attributes contained within the TGZ. Now, if you are requesting an array, now if you do not have specific array requirements, we would like to create the array ourselves, because we are going to create that array to best fit on a manufacturing panel. Now, if you specify an array, we will adhere to that, but that may affect your number up on our production panel, which in turn will affect your price at the end.
When is copper filled vias preferred over epoxy filled?
So all of our micro vias, we're going to do copper filled, but it is not preferred to do a copper filling on an actual buried via because it is very, very time consuming in our plating tanks and very difficult to get that copper to fill the entire length and width of that thickness of that final panel or sub. So we prefer to fill it with epoxy.
In your description of tinting, it looked like an additional layer was placed before the solder mask to keep it from flowing into the hole. I usually spec tinting as the lowest cost option. Is tinting or plugging the lowest cost solution for Summit?
As far as cost, that I believe plugging is a more cost effective method because when we actually tent them, we have to use dry film solder mask, which is using a different type of solder mask to tent that. Yeah, and we can tent with LPI, but it has to be a very, very small hole. If it is a larger hole, we will have to use dry film solder mask, which does add additional cost. Now, if we have to fill that hole with mask, that is no additional cost on our end. I hope that answers.
So I see
Oh, yeah, I'm looking Sal, I'm sorry, I was a little slow. Okay, okay, here we go. It's a rigid flex question. You should be able to answer this. All right, here we go.
Okay, for the cap core question, can you add the rigid flex caveat or both technologies? Rigid and rigid flexes preference is foil over cap core.
So yeah, for rigid and for rigid flex, foil is still the preferred option for both methods. Now, the biggest thing with rigid flex is we want to have enough Z axis between your topmost rigid flex layer and your outermost outer layer core. We want to have enough Z axis room in there to keep that foil solid, or even the core underneath solid, so we can keep that, and we can use our cocoon method to protect that flex through all of our manufacturing. Now, if you don't give us enough Z axis room between that flex core and that outermost rigid core, we can still manufacture it, but we have to manufacture that as an open pocket, is what we call it here, and we have to tape that flex before it goes through each one of our chemical processes, and it becomes very, very time consuming. But foil is still the preferred method.
Do stacked micro vias require the same multi-laminate steps as standard blind vias?
Yeah, for the most part, they do contain.
It's different.
They contain the same process steps, but they will go into different plating tanks because they will plate microvias in a different ratio.
No wrap.
And then depending on if there's wrap or no wrap required, right?
Laser views don't require wrap at this.
Correct. Yeah. So laser vias do not require wrap, where if they're on the outermost layer. So, and then our buried vias, they'll have to go through an extra plating process, right?
And have wrap required.
And have wrap required. Yep, that's correct.
I think that's all the questions.
Okay.
But wait, one more came in. What type of rework or repair is okay? Hang on, I'll drop this.
What types of rework or repair work are allowed for PCBs that do not pass test or quality checks?
So yeah, so most of our here at Anaheim, we cater mostly mill and aerospace, where repairs are actually not allowed. Meaning, if you have an open and two traces are not connected where they should be, we are not allowed to what you call weld and actually repair that connection. Now, a little bit of rework is allowed. So if you have a little excess solder mask, you can rework the solder mask. Or if you have a short, you are allowed to cut that short, but we are not allowed to repair, meaning reestablish a connection that was ultimately lost in our manufacturing process.
Right, and that this is Jerry. So that's kind of a key thing to understand between rework and repair. Rework typically means by continuing to process the board, you're bringing in the material to the condition it's supposed to be. So what does that mean? So if you have a short, you can keep on removing copper until you get the features the way you're supposed to. Where if it's an open, the copper that was supposed to be there has left. It's no longer there. So you're going to have to put something back that was part of the original buildup. And because you're putting something back, that falls under repair. So repairs are not allowed. Rework is. Usually if you're going to allow a repair, you have to give it an A-bus condition, AABUS, agreed upon between user and supplier.
Yep.
Somebody has a question. What is wrap?
Go ahead, Jerry.
You want to do wrap?
Yeah.
Okay. So
I'll let
wrap.
you explain it.
So this is wrap plating was necessary about the turn of the century. They were doing blind via and epoxy fill vias, and everybody would plate the hole, button plate it, epoxy fill it, get enough copper in the hole, and just planarize back to the original surface where the drill terminated on an epoxy filled blind or through hole, and then plate over it. This created a butt joint connection, meaning the barrel was never really wrapping onto the outer surface of the terminated layers that the drill was at. And during reflow, the barrel would expand and have which was a butt joint, and would separate, causing intermittent opens. So to solve the problem, what you see in the picture, thank you, Aaron, what you see here is a copper under a standard through hole. Copper goes in the barrel plated hole onto the surface of the board and naturally wraps. And we didn't have any problem with circuit boards that we built traditionally through hole, copper plated in the hole, wrapped onto the surface. Wonderful. When we started to planarize, we determined that copper had to go from the hole continuously onto the surface in order for it to be reliable. In about 2002, I think, wrap requirement was established. At that time, the copper has to go in the hole, 1 mil away from the hole, and has to be, at the time, 0.5 mil for class 3 and 0.2 for class 2 for IPC 6012. IPC 6018 always had class 2 and 3 at 0.2. And so IPC 6012 changed the rule based on a date, I believe. If the original date on the drawing is 2018, you only need 0.2 wrap for class 2 and 3. And this copper that goes over the surface would get plated on the final pattern plate on the outer layer, locking in the wrap plating from in the barrel that was 0.2 mil thick. Well, and then you plate copper on top of it. And this proved to be real reliable by decoupon testing, reflow, and thermal shock. This has always been proven true. What a designer should be concerned about, and what is a concern for us PCB fabricators, is when you put wrap over the surface of the starting foil, we now have to etch through more copper. There's more variation in the copper height because the wrap plating is not uniform at the end. So it becomes more difficult to consistently hit the feature sizes when you have wrap plating. When you do wrap plating for a blind via, a final epoxy fill, that's 2 wrap cycles. If you have a double blind, let's say you go from 1 to 4 and 1 to 8, and epoxy fill 1 to 16, then that layer has 3 wrap cycles and 3 additional cycles built up. So you have to take those into consideration. Do you have enough spacing, or do you want to put wrap over the dielectric? That's a great question. Thank you for asking.
Okay.
Hey, that's
Is there anything else?
There's a question about IPC 2581. Summit can receive it. I believe IPC 2581 is the newest revision of an XML data structured file format. I believe they're moving towards revision D on it. So there's revision A, revision B, revision C, and I think now working towards revision D. There's some challenges with the format. Everybody will output it, and many different software packages refuse to read other people's IPC 2581 versions. They're not necessarily backward compatible. So, and as a supplier, we have to keep on buying the newest revision of it that comes out. We've had many people look into the 2581. Very few pull the trigger on it. We can output stack-ups in IPC 2581, so you can read it into your CAD software.
Okay. So I think we have answered most of the questions. And again, we'll be emailing out a copy of this webinar. And I do want to remind everyone that our next webinar will be Thursday, September 25th. And the topic is IPC standards for quick turn prototype assembly. So if you already are getting our emails, you'll get a reminder, or on LinkedIn, we're always posting our webinars. So please be sure to register for that next webinar so you can attend. And if you have any further questions for any of us, you can reach out to us on our website and we can get you connected with an account manager that can help you get a stack up, help you get a quote, answer any of these questions or any questions that you might think of. So please reach out to us. We're looking forward to helping you with your next project. And again, thank you very much for joining us today. Thank you, Jerry and Aaron.
Thank you. Thank
Good
you for
job,
the
Aaron.
opportunity.
Good job, Allison. Appreciate it.